utilities and carbon footprint of various neutral hardening methods. Heat treatment service providers are being asked more and more frequently about their carbon footprint. The neutral hardening process is an ideal baseline for comparing atmospheric and vacuum equipment emissions and costs. This topic compares calculations, collected data regarding various equipment. Please help welcome the speaker, E.J. Bernard.
Welcome. Good morning, everybody. Thanks for showing up bright and early. I really appreciate it. I'm sure many, I don't know how many of you went out late last night. So just like 2 talks this morning. But so I'm all ready to show you guys how we calculate carbon footprint for heat treat. This is something that's coming up a lot more for me personally. I have a lot of customers and a lot of regulatory agencies, talking with IEA. We're all looking at ways that we can help heat treaters in the thermal processing industry in general to determine what their carbon footprint is. And there's a lot of surprising results that you wouldn't normally expect. There's a lot of easy answers out there of what things are. And what I was hoping to do with this presentation is show some of the numbers that go into calculating your carbon footprint, and then have everybody figure out for themselves what their numbers are. So basically, just to start off with a couple things, the greenhouse gas initiative, which what EPA follows, puts greenhouse gas or carbon emissions into 3 scopes. Scope 1, which is primarily the fossil fuel use you use in your plant. Okay, that not only has to do with natural gas, that also has to do with vehicle emissions, and then the other carbon bearing, any other carbon bearing fluid or gas that you're using in the fuel. Scope 2 has to do with electric usage, primarily. It also has to do with steam usage or heat usage if it's purchased. Okay, so whatever you bring into the plant, that is part of Scope 2 emissions. Most carbon accounting methods will only require you to look at Scope 1 and Scope 2. However, Scope 3 is where the predominant amount of carbon emissions is located, and that has to do with transportation, but also atmospheric gas usage, which can be a tremendously huge part of your carbon footprint in the heat treat. So, whereas most people will tell you to look at Scope 1 and Scope 2, Scope 3 is very, very important for what we do. So I'm going to be going into that as well. The other thing you have to remember is there will be hearing probably some new presentations today about what you need to do. Just eliminating certain fossil fuels from your plant doesn't exactly make sense, but you have to replace it with something. You have to replace it with something like hydrogen, which you might hear about today. You might have to replace it with electric power. Knowing the carbon footprint of each one of those is very, very. So, that said, trivia question, first time in the morning. What's the most abundant greenhouse gas in the atmosphere? Water. Boom. Water vapor is in clouds is the number 1 greenhouse gas. There's, on average, 1% water vapor in the atmosphere. Water vapor is a gas that attracts and absorbs radiation and traps radiation in the atmosphere. You get up to about 2.5% water vapor at a 70-degree muggy day, 100% humidity. But water vapor, as it is not long-lived in the sense of greenhouse gases. When we get into the long-lived greenhouse gases, we're talking about carbon dioxide, methane, and some other gases. But this is from my presentation in about 45 minutes from now at the IEA Combustion Seminar, where gas radiation is very important in heat treating, understanding how gas radiation plays. And water vapor and carbon dioxide in a furnace is very helpful to transmit heat to the workload. Sulfur dioxide is another one, but also that's not long-lived. You might hear ozone. Ozone is a greenhouse gas, but at the same time, it's not as long-lived as other things, and it can be interacted with other things. But mostly nitrogen, hydrogen, oxygen, all the diatomic gases are not greenhouse gases. They're transparent to radiation. So the 7 major greenhouse gases are these: carbon dioxide, methane, nitrous oxide, and all your fluorocarbons, sulfur hexafluoride, which is in heat treating might be used in magnesium for cover gas. I've seen that. Nitrogen trifluoride I don't see very much used at all, but the HFCs and PFCs is what you're going to see in air conditioning for the most part. So that's actually a huge thing. If air conditioning leaks are a part of what you're doing, it's a major greenhouse gas emission. Methane is about 25 times the impact of carbon dioxide. In this presentation, I'm only going over carbon dioxide. Methane in general, unless you have leaks in your piping and everything else like that, is going to be a smaller portion of what goes on. Nitrous goes along with NOx, if you have NOx in your plant, but again, the impact is relatively small for what we do, so I'll be ignoring that for right now. So, carbon dioxide in the atmosphere. Back in, before the pre-industrial revolution, we had about 275 ppm in the atmosphere. In 1960, that grew up right about 335, 340. So right now we're about 420% ppm per carbon dioxide in the atmosphere. Okay, that's happened. It's part of what we do. Well, what does it mean? Over time, we've also seen the land-ocean temperature index, which is how we pretty much track the heat temperature of the Earth, has risen as well. I mean, correlation does not apply causation, but the lines track each other. Okay, so whether you believe in global warming or not, doesn't matter. This is what it is. This is what the regulatory commissions are setting up to help fight, and we're trying to all get to net zero. And the one thing that's important is understanding, if I can get the layer, our natural removal rate. Yes, it's estimated our natural removal rate of carbon in the atmosphere is 17.5 gigatons of CO2 per year. Right now, we're about 35, so we need to get down to about 17.5 to be net carbon neutral, okay? So, that said, U.S. industry's pretty much doing their part. We're pretty much flat over the last 30 years. You know, flat to declining. Of course, we had the COVID year here, which kind of impacts things a little bit, but in general, we've been doing it. And over time, industry has reduced our carbon emissions by 13.7%, so, which is pretty good. So now we need to get down about 50% from here, but again, that for the U.S. is doing their part. The rest of the world, not so much. Let's just be honest, okay? So there's things we can do, there's things that the U.S. is doing, there's things the rest of the world is doing, but all we can control is what we do. And first of all, we need to know is what is our footprint ourselves. So to calculate your carbon footprint, I kind of put it into 5 steps. Step 1, find your natural gas bill. It's the easiest thing to find. You can hook up gas meters, every one of your furnaces, everything else like that, doesn't matter. You know what your natural gas bill is in your plant. Okay? Step 2, find your electric bill. Same thing, you can hook an electric meter to every furnace you want, go for it, and that's probably the preferred way to do it. But if you don't have that, you got it. You got an electric bill, you got a gas bill. Number 3, find your POs, find how much atmospheric usage you use per year, okay? How much nitrogen, how much hydrogen, how much argon, how much ammonia, how much methanol, acetylene, any other purchased gas that you're putting in a heat treat process, okay? 4, heat treating is heavily dependent upon trucking. Read your odometers. This is not a small part of your carbon footprint. You need to know what that is. And then we're going to evaluate other categories, which in the end gets way down the chain. This is the top 4 are probably the top issues in heat treat. So, natural gas, pretty easy. Find how many 100 cubic feet or 1,000 cubic feet you use over the course of the year. Multiply it by 0.05444. That's it. That's your carbon footprint of your natural gas. So I have here units of metric tons of CO2 equivalent. That is, if you're going to go out in the market and buy carbon credits, or you're going to have carbon taxes or have carbon offsets, all these fancy terms, all of them are issued in metric ton CO2 equivalents. So I'm going to try to get all these numbers there. If you have in kilograms CO2, multiply by 1,000. If you have pounds CO2, you multiply by 2,204, 2,205, and you'll get to the same number, okay? So that natural gas, that's pretty simple. Getting to electric, this is where it gets a little bit different. Electric bill, by how many kilowatt hours you use, multiply it by a number called the emission factor, which I have EF here, and then you'll get your metric tons of CO2 equivalent. So what's an emission factor? It is a number that depends upon where you are, how your power is made, and what country, basically what country you're in. So in here we got here, location based. In the US, this is what EPA says the carbon footprint of your electricity is by your emission factor. Here in Indiana, we're in RFCW. So that means our total output is 0.4468 would be our emission factor. Okay? If you're in, let's say, Michigan, you're going to be 0.523, which is higher, right? It's interesting because the New England states have entered into what you call, not a cap and trade, but a cooperative to help reduce carbon emissions. The New England states, the 10 states that are up there, actually have much lower emissions. But on average, the US is 0.3712. So Michigan and Indiana, for example, are much higher than that US average. All right. If you're going to do this, and this is basically in kilograms or metric tons of CO2 per megawatt hour, is kind of the conversion rate. So if you want to do this, all you have to do is go find this US EPA emission factor greenhouse gas inventories, which is publicly available on the internet, and you'll find this map and you'll find this list. You'll also find a factor I used this before. Globally, electric emission factors, where you are in the world, it's interesting. I did this in relative emission factors to make it easy to read. The United States is the one. Canada uses about 1/3 carbon for electricity as the US. Mexico is about 1.05. Right? One thing about Mexico is they have a lot of oil, whereas we have a lot more natural gas, but it's still, the impact is there. France, they're heavily nuclear. So they're only 16% of where we are in the United States. Sweden is pretty much 100% renewable at this point, 0.03. So their carbon footprint of their electricity is much less. Now, there's a lot of countries who want to get to that, but they're very far from that right now, especially here in the United States. China, 1.5, most of it's coal, most of it's very bad coal. And so India is the same thing. And it surprised me, I put Japan here because I was surprised that Japan was that high. I thought it would have been much less. So it also has to do with your fuel. So in general, coal is about 1 on your carbon footprint emission factor. Natural gas, and this is a number I'm going to use throughout this presentation just because in the US it seems like a good baseline to calculate a carbon footprint is 0.411. And if you're going to do this in pounds, CO2 is 0.91 pounds CO2. So that's the number I'm going to be using throughout this presentation to compare, since a lot of times we're comparing natural gas firing, and then we might as well compare it to how making electricity using natural gas, right? So now, if you get a contract with a solar power plant or a wind power plant, all these numbers are going to be 0, right? But until you get that, this is where we're at. Other thing to keep in mind is furnace efficiency versus electric utility efficiency. In general, the best natural gas power plants are 44% efficient. Okay? But a natural gas furnace, just say at 2,000 degrees, if it has recuperation, it's going to be in these red lines. If it's just cold air combustion, it's going to be in the gray lines. This gold line is electric efficiency. If you're using all electric efficiency of the US, including all the solar and geothermal and nuclear and coal and everything else, it's going to be about 49%. So if you're putting power into your electric power into your furnace, you have to be at 44 to 49% combustion efficiency or more to make it worthwhile on a carbon footprint basis. It just so happens that most processes that are from 1750 and below or 2000 degrees and below are going to be there. So if you're looking at that, that's how you would kind of understand on an apples to apples basis which one's better, electric or natural gas for my application. Because one thing we don't want to do with our greenhouse gas emissions is make a problem worse. And with that, and there's a lot of talk about electrification, which is good, but if you're in an area of the country that has a lot of combustion-based power, use natural gas. If you're in a highly hydroelectric area, it's like TVA section, if you're getting power from Quebec, if you're right next to an Iowa wind farm, go electric. It's that simple. Okay? It doesn't matter. Just take a look at where your power source is coming from. But if you blindly switch one to the other, you could be making a problem worse by going to electric. The other thing to remember is typically when you're converting from natural gas to electric, more times than not, you have to derate your furnace, the production rate of your furnace. So because you can't fit as much electric elements to replace the gas firing in that furnace. You will, if you're converting old technology, buying a new furnace, that doesn't matter. It will take up more space, but if you're trying to retrofit a package, that's what's going to happen. Other thing to keep in mind is the losses before it gets to the plant. Natural gas and distribution, you lose 7.5, before it gets to utility, you lose 7.5% natural gas from the wellhead to utility. You lose about 8.5, excuse me, 7.6, 8.5 from the wellhead to your manufacturing plant. Just gone. Leaks through the pipelines, through valves, everything else like that. Electric power distribution, you're losing on average 5 to 6% on the power lines. So if you're going to do a complete accounting, you have to consider these factors as well. Other thing to keep in mind, and this is becoming a bigger issue, is power factor. You actually build more kilowatt hours than you actually use. Utilities bill you a gross up for your power factor. So while your furnace only might use, for example, 1,151 kilowatts, they're going to bill you for 1,257 based on the power factor in your plant. Power factor is based on your inductive loads. So if you have an induction machine, if you have a lot of motors, very high power motors, your power factor is going to go down from 1. Increasing the power factor closer to 1 is very important because that will reduce your electric bill and thus your carbon intensity as well. So on to atmospheres. In the scope 1 and scope 2 are all these. They're already accounted for. Because you make your on-site atmospheres from natural gas, you make your on-site atmospheres from electricity. Okay? So these have already been accounted for. But then you have to take a look at your cryogenic gases, your bottled gases, and what your use is to really know and you have to know what their carbon footprint of those gases are before they get into your plant, because they all have one, okay? And for you to really understand what your carbon footprint is, you gotta know what that is. So let's take a look at nitrogen. Okay, and here I'm comparing, this is a calculation, say I'm gonna use 6,000 SCFH of nitrogen in my continuous furnace would be a good example of this if you've got a blanket of nitrogen going through it, right? And let's say I have just about 7 days of capacity in my tank. That's kind of what that is. I have a vent rate for my tank, so my tank is venting about 0.5% of that gas per day. Maybe 0.2 to 0.5. If you're doing any more than that, you got leaks in your piping, you better go find them, okay? So in general, and then you have to take a look, how far is the nitrogen coming from and how is it getting there? Most of the times it's delivered on truck. For surface, we get ours here for Indiana, not very far from here, so maybe it's 50 miles away from Indianapolis. For surface, it's 300 miles away. So that's being delivered on a truck using diesel fuel. I mean, it's not all electric yet. So in the end, if you take a look at everything, the carbon footprint is about 56.43 kilograms CO2 per hour. Now, depending on how you can gross that up, you can multiply by whatever number of hours per year you want, 6,000, 8,760, depending on how much you're using, but that's kind of the thing. Over here, I kind of took a look at the technology available for pressure swing absorption and membrane on-site nitrogen, just kind of giving an understanding of what other methods that you could make nitrogen at your plant. So cryogenic is right here at 99.59s, and then you've got on-site PSA would be the red bars, and you got some on-site membrane, two different on-site membrane technologies would be the other 2 bars. Hydrogen has a lot of different colors these days, and the predominant method, blue hydrogen is where everybody's trying to get to. We actually have a blue hydrogen project. We actually have a gold hydrogen project right now because we get into some high advanced gas chemistry things. We're actually making this stuff. So these are all the different colors as far as I know. This is from McKinsey, so it's pretty robust. But it also shows you what the emissions rate of the different technologies are. 77% of hydrogen produced in the United States is gray hydrogen. So most likely, if you have using hydrogen in your plant, it's coming from the gray hydrogen route, okay? Which is going to emit 0.02411 kilograms CO2 per standard cubic feet. So if you want to multiply, it's 24.11 kilograms per 1,000 cubic feet, okay, of hydrogen. So if you know your usage, say if you have 6,000 cubic feet an hour, like we just talked about, it's about 205 CO2 kilograms per hour. Now, as we get into more efficient ways of producing hydrogen, that number will drop, but at least it's not getting it from coal, which used to be the predominant way of doing it. Now it's from natural gas. Hydrogen for heat. A lot of people, you'll hear about this today. Today, as of right now, is not a good idea because your carbon footprint goes up because you're using gray hydrogen. As you use more renewable methods to make hydrogen and start blending hydrogen into the natural gas lines, it will bring the carbon footprint down, but as of right now, that's not the case. You have to reduce, basically you're going to increase by almost on a factor of 50% by going to hydrogen right now. Other steam methane reforming is what's used to make hydrogen. There are other atmospheres made from steam methane reforming, predominantly ammonia. Okay, and that would be the carbon. That would be the emission factor for ammonia. Methanol is also made predominantly from steam methane reforming. So basically, you're using 2 kilograms for every gallon of methanol you use. Then you have the burn off as well. Acetylene, there's 2 routes. Primary route is the calcium carbide route, which is probably what most people are getting into their plants. The other one's the steam methane reforming or autothermal reforming. So calcium carbide, you got 0.529 kilograms per standard cubic feet of acetylene to produce it. And then when you burn it off and everything else, that's something else. But the thing is also you have to remember when you burn off, you should burn off acetylene, because if you don't, it can form methane. And if you form methane, then you made your problem 25 times worse, right? So you make sure we have to make sure we burn it off at the end of a vacuum carburizing or low pressure carburizing cycle. And again, there's greener methods for each gas available, but they're not in high enough numbers to make an impact for our industry yet. Go to someone else first. So here's just an example of a calculation between RX, endothermic atmosphere, versus nitrogen methanol. Just kind of using the numbers we just presented. So if you're using gas firing or electric, okay, to heat the gas, this is for 400 standard cubic feet per hour of endothermic gas. So whether it's made from nitrogen methanol or made from RX, it's 400 cubic, and we're at a 1700 degree furnace. So the feedstock, when it comes out of the generator, RX has 4.76 pounds of CO2 per hour if it's made using natural gas heating. Electric heating is going to be about the same, might be a little bit more, a little bit less, depending on your electric heat source. Nitrogen methanol, when it comes in, is 7.82, just because of the flow rate of what's going on. Then you have to crack methanol in the furnace, which ends up as an additional heat load on your furnace. So you have to, that energy goes into the calculation here. Then to heat the gas from more or less 77 degrees to 1750 degrees, it's going to take a little bit more heating. And we're just assuming about a 61% efficient furnace at 1750, so something with recuperation. And then eventually we're going to burn it off, okay? Because we're not just going to emit CO into our plants and put it up the stack. We're going to actually burn it off, and unless we really want, unless we have a really good suction device, we can get it out of there some other way. So the total pounds of CO2 per hour that we're going to produce for 400 CFH is right here. So in general, nitrogen methanol is going to be more emissive than RX atmosphere. Again, this all has to do with what electric rates you use for emission factors, but more or less, this is where we are today. All right. So considering different furnace types, and this is where we get into comparing neutral hardening methods. Furnaces are designed for a process. Not every furnace is designed to do all processes. You can have a furnace that's doing a process that is not meant to do it, right? So the primary use is a big factor in how efficient a furnace is, because it's usually designed for a certain maximum temperature rating, and it's usually designed for a certain amount of you're gonna design a single chamber vacuum furnace for fast cooling most of the time. or you're gonna design it with an all-metal hot zone so that it purges easily, so you don't have any residual water vapor. An atmosphere furnace that is meant to be high production, you're gonna have 2 chambers, so you have a hot chamber always hot and a cold chamber always cold, so you're not heating and cooling the chamber all the time, and retaining heat within the chamber from process to process. And then for vacuum versus atmosphere or air, I mean, it's going to be vacuum's not going to have any atmosphere, right? But it still does have a pump, right? In general, 17.5 kilowatts is going to that pump all the time. And then batch versus continuous. Continuous is helpful in carbon footprint because all the losses are a steady state in the furnace, which means the wall losses, so all the refractory is going to be soaked out and you'll be at a minimum there. But if you have natural gas heating, a lot of your heat's going up through the flue. When that is the heat to heat the products of combustion, CO2, water vapor, nitrogen, oxygen, if you're at excess air operation, to heat them up to the atmosphere, to the temperature that your process is at. So using recuperation, regeneration, other thermal efficiency techniques drives that number down, so we all have to keep that in mind. So for example, I have here just taking a 1,000-pound load of steel. I'm not accounting for trays or anything else like this in here, just trying to make this as simple as possible. So we have 2 different atmospheres, RX versus vacuum. This is the rating of each furnace. Now the furnace, this rating is going to be a big deal here. This is about 1.2 million BTUs. I'm estimating about 3648, 36 load here. And this is just general numbers for what I've seen, what furnaces we make, and what I would see out there in the industry. So this would be similar to an all-case furnace, whether it be gas-fired electric. Here, we can't get as much heat into that furnace when it's electric as when it's gas-fired on a gross basis. On a net basis, it gets a little bit better because you have flue gas losses, okay? So in general, the flue gas, this is what the net rating of that furnace after accounting for flue gas losses up the stack. Wall losses, a hot wall furnace is going to have much lower wall losses because you have so much refractory. In general, a well-insulated hot wall furnace, which is a refractory line furnace, is going to be 150 BTUs per square foot per hour loss rate. Really efficient furnaces are about maybe 135. But for vacuum furnaces, especially single chamber vacuum furnaces with a lot of nozzles in them to promote wind flow, they can have a lot higher values of heat losses on general. But then if you have a 2-chamber furnace, you can design the furnace with much lower heat losses because the hot chamber is always hot. You don't have to heat and cool the inner chamber all the time. Because you have more resistance to cooling, the more energy gets trapped in that inner chamber. So in the end, we have our max heat to load. Max heat to load leads to how fast can we heat it, right? So the more max heat to load leads to the faster heating times, right? So in general, for a 4,000-pound load, this is how much time would you take to heat for each one of these scenarios, okay? And then let's say we're going to soak for 60 minutes, so we have to overcome wall losses and atmosphere losses and other things for about 60 minutes as well to kind of get a uniform temperature within the load. So in the end, this is how much heat energy you're using. This is how much energy is going through the walls. This is how much energy is going to the atmosphere. This is how much energy is being stored in, say, an inner chamber that eventually will come out of the inner chamber upon quenching. Okay, then here's your RX flow, here's your RX usage, your nitrogen usage. I'm assuming about a 10-bar quench here. For 4140, 1570 is a neutral hardening method of choice. 10-bar quench could or could not get there depending on your furnace setup, depending on the cross-section of parts. But in general, that's what I'm using there to calculate that. And then you have to consider how much electric power your motors are using over the course of the cycle as well. So in the end, hot wall gas fired, you're using from natural gas is emitting 25.04 kilograms CO2. That's from that first calculation, just multiplied by 0.05444. Electric footprint, again, I'm using natural gas firing power plants here. So this number is going to go up or down depending upon where you are in the country or where you are in the world or what thermal source you have. Obviously, it will be 0 if it's solar, wind, geothermal, well, not geothermal, but because it has a tiny carbon footprint, but nuclear as well would be 0. So that would change the numbers drastically. This is a footprint for using Arctic's atmosphere, and this is a footprint for using the amount of nitrogen you're using. And all in all, this is a different carbon footprint of each process. That's basically it. So, and then there's numbers you can play around with here. You can have, you can increase your electric capacity in your furnace. You can decrease there's a lot of numbers you can play with here that aren't exactly, so these aren't exactly set in stone. There's a lot of variables, but in general, if you're going to just do a calculation, here's a place to start, and then your mileage may vary depending on your particular situation in your facility, wherever you are in the world. Other things to do to reduce carbon footprint, tune your burners. There's too many burners out there that are untuned. You got to get them to 5 to 10% excess air. Repair your cracks and gaps and broken insulation. Clean your heat exchangers. These are all energy efficiency things that reduce the amount of energy you use, which will then eventually make you reduce your carbon footprint. Focus on energy efficiency. Focus on increasing production per pound of CO2 released, or per kilogram of CO2 released, or metric ton of CO2 released. That in general will lower your carbon footprint compared to someone else. Preheating loads is a major way to reduce your carbon footprint. Power factor, evaluating that is critical, especially with any furnaces that have large motors. Okay? And then alternative production methods. You go buy a new furnace, use different technology, but of course, these things are pretty much the cheap and easy ways versus this is the hard and expensive way to take care of things. Trucking, major factor in heat treat. It's this is just, if you're going to truck something, you're going to emit 1.45 kilograms per mile. So however far you're getting your loads from, or however far you're delivering them back to, you have to take that into account as a heat treater, because all the heat treaters, should not say all, most heat treaters have truck fleets. Okay, and they're responsible for getting the parts sometimes to and from a customer. So you have to take a look at their truck, the truck content, and how far your trucks have gone through the year to figure out what impact that has. All right. So the farther you are away from your customer, the larger that number is going to be. Light duty truck trash and charge, put that for completeness. Some of these standards want you to calculate the how far your employees commute every day. And that's actually, for some companies, that's not insignificant. So you see a lot of people working from home, and for a lot of green companies, that's going to stay that way because they don't want to deal with the emissions from people commuting. Other categories to consider: HVAC. All usage and leakage. If you're leaking out your HVAC system, that's a really bad thing. You want to take a look at that. A lot of control cabinets and heat treats are air conditioned, so you want to make sure you take a look at those too. Other purchase goods and services. Quenchants, I didn't really consider here. It's like oil quenchants. A lot of oil quenchants are recycled, to be quite honest. They're heated a little bit, but the impact on heating is not that big of a deal. But they do have a carbon footprint when they come into your plant, and depending on your usage, they have, but most of the time you're not burning them off. They have drag out and things like that, so you have to replace it, but you can also recycle it and get it back again. So the impact isn't very high. Water is a bigger deal. There are wastewater emission factors, because to treat wastewater, it takes a lot of energy and it takes a lot of gases. So you have to keep that in mind. Waste generation, business travel, community. But then this is where MTI can get involved. Downstream processing, use, end-of-life treatment. To me, it's just what we do as heat treaters reduces carbon footprint, because I wouldn't want to drive around with a gear that was not heat treated. I wouldn't have a very long life of my car. I wouldn't have to replace the part a lot more often. I would have to not get as much power to the wheels. So what we do is very important on a carbon footprint basis. So all the carbon we put in, I'm not going to calculate, but I think the carbon, it reduces on the way out. But that's for someone else to calculate than me today, right? Other thing, just want to make a quick mention, there are ways to offset what you emit. in the carbon, and there's renewable energy credits that you can buy from your utility to get green power. You can buy green power just direct off the market. So you can ask your utility about both of those. Carbon offsets, you can buy these. Right now, they're about $8 to $13 per metric ton CO2e, okay? In general, 1.1 million BTUs per hour of natural gas. If you're just going all year, 87, 60 hours, you're going to emit 465 metric tons of CO2 per year. So you buy offset without carbon, it's going to cost you $3,700 to about $6,000. So which in general is not a lot. So I mean, if you're in a heat treat, if you're going to tell me I can run my furnace and spend $6,000 a year, that's probably not a bad deal. But then it happens to be carbon taxes, which is not something you purchase, something that's put up on you. It's about $8 most places too. It's scheduled to go up about 50. That's the prediction. But even then, it's not going to be very much. You can talk about carbon sequestration too, but that's not near us right now. Yeah. And so that's basically it. So I thank everybody for your time. I know we have to move on to the next speaker, but I'm here at the booth, at Surface's booth. If anybody has any questions, I'd be happy to take them a little bit later. So thank you very much, everyone.